Hey everyone, welcome back for another deep dive. You know we love to dig into the research you share with us, and today's topic is no exception. It's all about learning, but more specifically, it's about how we can learn effectively. I think we can all relate to that feeling of being overwhelmed when we're trying to learn something new.
Absolutely. And this deep dive is really going to be your guide to understanding how to make learning stick, how to learn smarter, not just harder, and really avoid that feeling of overwhelm.
So, we're going to be unpacking this idea of cognitive load, a concept from educational psychology that helps explain how our brains handle new information.
Right. And the core idea here is that our working memory, that part of our mind where we actively process information well, it has limits. It's like a mental workspace that can only hold so much at once. And when we overload it, that's when learning starts to suffer. But it's not just about the sheer amount of information.
It's also about the type of mental effort involved, right? Like some things just naturally feel harder to learn than others, even if they don't seem longer or more complex on the surface.
Exactly. And that's where cognitive load theory comes in. It helps us understand these different types of mental effort and how they impact our learning. The paper we're diving into today, John Sweller's 2010 work, Element Interactivity and Intrinsic, Extraneous, and Germane Cognitive Load, gives us a really clear framework for thinking about this.
And this paper introduces this concept of element interactivity, which sounds kind of technical, but is actually a really powerful way to understand how our brains deal with information.
It is. And Sweller really uses this concept of element interactivity as a unifying idea to explain all the different types of cognitive load. So let's start there. What exactly do we mean by element interactivity?
Yeah, I think that's a great place to start. What is it? What's it all
Mhm.
about?
So in simple terms, element interactivity refers to how interconnected the different pieces of information or elements are that you're trying to learn. It's all about how much those pieces need to be processed together in your working memory. And these elements can be anything: individual facts, so steps in a process, concepts.
Okay, so I'm picturing like puzzle pieces. Some puzzles have pieces that are pretty independent, while others have pieces that really interlock and depend on each other. Is that kind of what we're talking about here?
That's a great analogy. So let's say you're trying to memorize a list of random words. Each word is an element, but they're not really related to each other, so you can learn them one by one without too much trouble. That would be an example of low element interactivity.
Okay, so each word is like an independent puzzle piece. Got it.
Right. But now imagine you're trying to understand, say, how photosynthesis works. You've got sunlight, water, carbon dioxide, chlorophyll, sugars, chemical reactions. All of those are elements, but they're all very much interconnected. You have to understand how they all work together to get the big picture.
Yeah, you can't really understand one part without considering the others. It's like a complex machine where all the gears are turning together, so that would be high element interactivity, right?
Exactly. And the higher the element interactivity, the more demanding it is on your working memory
Yeah.
because you have to hold more pieces of information in mind simultaneously and see how they relate.
Makes sense. So, how does this idea of element interactivity tie in with the different types of cognitive load?
Well, it's actually the key to understanding all three types:
Yeah.
intrinsic, extraneous, and germane. So let's start with intrinsic cognitive load. This is the inherent difficulty of the material itself, determined largely by, you guessed it, element interactivity.
So, if the elements are tightly interwoven, the intrinsic load is going to be higher because our brains have to work harder to grasp those connections.
Precisely. And here's the thing. For a given learner, for you, given your existing knowledge and skills, the intrinsic load is pretty much fixed. You can't really change how complex the material itself is.
Okay, so we can't change the inherent difficulty, but understanding it can help us know what we're up against, right?
Absolutely. If you recognize that something has high intrinsic load, you might need to break it down into smaller chunks. Maybe focus on understanding the key relationships first before getting into the finer details.
Okay, so that's intrinsic load, the built-in complexity.
Mhm.
What about extraneous cognitive load? It sounds like that's something we might have a bit more control over.
You're right. Extraneous cognitive load is all about the unnecessary mental effort that we have to expend because of how the information is presented to us. It's not about the complexity of the material itself, but rather the complexity that's added on top because of bad design, confusing instructions, or just poor organization.
So it's kind of like mental clutter that gets in the way of actually understanding the core concepts.
Exactly. And the interesting thing is, extraneous cognitive load also arises from element interactivity. But this time, it's element interactivity that's unnecessary for understanding the core material. It's like you're being asked to assemble a puzzle, but the instructions are all over the place, and they make you jump back and forth between pages for no reason, or they give you extra pieces that don't even belong.
I can definitely picture that. Suddenly, you're not just focusing on the puzzle itself, you're also having to deal with all this extra stuff that's just making it harder.
And that's exactly what extraneous cognitive load does. It adds unnecessary mental work, and that drains your cognitive resources, leaving you with less brain power to actually learn what you need to learn.
So it's like wasting mental energy on things that aren't helping us understand the core concepts.
Exactly. And the paper dives into some classic examples of how this happens. It talks about these cognitive load effects, and they really illustrate the point beautifully. Let's start with the split attention effect. Have you ever tried to follow instructions where the text is on one page and the diagram is on another?
Oh, all the time. Especially with like furniture assembly instructions, you're constantly flipping back and forth trying to match the words to the pictures.
And that's the split attention effect in action. Your brain is forced to mentally integrate these spatially separated but related pieces of information. You have to search for the corresponding parts, hold them in mind, and then try to link them up. And that creates all these unnecessary interacting elements, this mental juggling act that takes away from actually understanding the task itself.
Right. So it's not that the task itself is necessarily complex, it's that the way the information is presented forces us to do all this extra mental work.
Exactly. Now imagine if those instructions were designed so that the labels and explanations were right there on the diagram itself. No more flipping back and forth, no more mental searching. The related elements are integrated, and that reduces extraneous load.
Okay, that makes a lot of sense. So basically, good design should aim to reduce the need for that kind of mental gymnastics by presenting information in a way that minimizes unnecessary splitting of attention.
Absolutely. Now, another common culprit of extraneous load is the redundancy effect. Have you ever encountered learning materials where they say the same thing in multiple ways? Maybe a long written explanation followed by a diagram that illustrates the exact same points.
Oh, yeah, I've definitely seen that. It's like they think if they repeat it enough times, it'll magically sink in.
Right, but the problem is, it often backfires. Because now, instead of just focusing on understanding the concept, your brain might start trying to compare those different representations, trying to reconcile them, even if they're saying the exact same thing. And that's just adding unnecessary processing.
So it's not that repetition is always bad. It's that we have to be careful about how it's done. We want to reinforce understanding, not create extra work for our brains.
Exactly. Sometimes less is more, especially when it comes to extraneous cognitive load, and the goal is to present information clearly and concisely without unnecessary repetition or redundancy.
Okay, so we've got split attention and redundancy. Are there any other common cognitive load effects we should be aware of?
Yeah, there's a really interesting one called the goal-free effect. Now, this one might sound a little counterintuitive, but bear with me. It basically suggests that in some situations, you can actually learn more effectively if you're not given a specific goal to work towards.
Wait, so you're saying that not having a clear objective can actually be better for learning? How does that work?
Well, think about how we usually approach problem solving. We have a goal in mind, and we're constantly evaluating our progress towards that goal. We're thinking about where we are, where we want to be, and what steps we need to take to get there. This is called means-ends analysis.
And that involves holding a lot of information in mind at once, right? Comparing, analyzing, strategizing.
Exactly. And all that mental juggling can actually create quite a bit of extraneous load. Now, with a goal-free problem, you're not fixated on reaching a specific endpoint. Instead, you're encouraged to explore the problem space more freely, to play around with different ideas and see what you can discover.
So it's more about exploration and experimentation than about reaching a predetermined destination.
Precisely. And because you're not burdened with that constant goal evaluation, you can often focus more deeply on the underlying principles and relationships within the problem itself. And that, in turn, contributes to germane cognitive load, the effort that actually leads to deeper understanding.
Okay, I'm starting to see how that could be beneficial, especially if you're dealing with a new concept where you need to really grasp the fundamentals before you can start applying them to specific goals.
Absolutely. Now, another powerful effect, and one that I think many of us have experienced firsthand, is the worked example effect. This is all about the power of learning from fully worked out solutions, especially when you're first encountering a new type of problem.
Oh, I definitely remember those from math class. Seeing how someone else solved the problem before trying it myself always helped me understand the steps better.
And that's because worked examples reduce the need for that means-ends analysis that we talked about earlier. When you're trying to solve a problem from scratch, you have to explore all these different possibilities, many of which might be dead ends. But with a worked example, you can focus on understand the logic and the reasoning behind each step of the solution.
It's like someone's showing you the path through the maze instead of making you find it yourself.
Precisely. And that reduces extraneous load by eliminating all those unnecessary explorations and dead ends. Instead of wasting mental energy on trial and error, you can direct your cognitive resources toward understanding the why behind the solution.
Okay, that makes perfect sense. So it sounds like all of these cognitive load effects, split attention, redundancy, goal-free, worked example, they're all pointing to the same underlying principle, minimizing unnecessary element interactivity.
Exactly. That's the central message here. Whether it's through integrating visuals, removing redundancy, using goal-free problems, or providing worked examples, the goal is to reduce the number of elements that learners have to process simultaneously that aren't directly contributing to understanding the core material. It's about streamlining the learning process to make it more efficient and less overwhelming.
So we've talked about intrinsic load, the inherent complexity, and extraneous load, the unnecessary complexity. Now, what about germane cognitive load? Is that like the good kind of mental effort?
You got it. Germane load is the effort that's directly devoted to making sense of the material, to building those deep connections and understanding. It's the mental heavy lifting that actually leads to learning.
So if intrinsic load is the weight of the material itself and extraneous load is like adding extra weights on top, then germane load is the muscle we're building by lifting those weights.
That's a fantastic analogy. And here's a really important point that the paper emphasizes. Germane load isn't a separate source of load, like intrinsic or extraneous. Instead, it's the destination for your cognitive resources. It's where you want your mental energy to be directed.
Oh, okay, so it's not like we have a limited supply of germane load. It's more about how much of our available mental capacity we can channel towards that deep processing and understanding.
Precisely. And the key is that if we're bogged down by high extraneous load, if our working memory is cluttered with all those unnecessary interacting elements, then we simply have fewer resources available for germane load.
Right. If we're spending all our mental energy on navigating confusing instructions, we have less brain power left to actually grapple with the core concepts.
Exactly. That's why minimizing extraneous load is so crucial. By reducing that unnecessary mental clutter, we're freeing up our cognitive resources to engage more deeply with the material.
It's like clearing our mental workspace so we can focus on the real work of learning. Now, the paper also talks about this thing called the element interactivity effect, which sounds kind of intimidating. What's that all about?
The element interactivity effect basically highlights the fact that extraneous cognitive load has a bigger impact when the intrinsic load is already high. In other words, if you're dealing with a complex topic that already has a lot of interacting elements, then poorly designed instruction is going to hit you harder.
So it's like if you're already carrying a heavy load, adding even a small amount of extra weight can make a big difference.
Exactly. The paper gives the example of learning a new scientific vocabulary. If each term can be learned somewhat independently, then even a poorly designed vocabulary list might not completely derail your learning.
So if the material is inherently simple, we can kind of power through some bad teaching.
To a certain extent, yes. But now imagine you're trying to understand a complex scientific theory, where everything is interconnected and builds on previous concepts. In that case, if the instruction is poorly designed and adds unnecessary complexity on top of the already complex material, it can make it incredibly difficult to learn.
It's like trying to build a house of cards on a shaky foundation. It's just not going to work very well.
Exactly. So the element interactivity effect reminds us that we need to be especially mindful of extraneous load when we're dealing with inherently complex topics.
So it's all about being strategic, knowing what we're up against, and choosing the right tools and approaches for the task at hand.
Absolutely. And that leads us to another really interesting point that the paper discusses.
hmm
How our level of expertise changes how we learn best.
So as we become more knowledgeable in a particular area, what worked for us as beginners might not be as effective anymore.
Exactly. The paper talks about the expertise reversal effect, which describes how instructional techniques that are highly beneficial for novices can actually become less effective or even detrimental for experts.
Okay, that's fascinating. So what might be helpful at the beginning can actually become a hindrance later on.
Exactly. Think about worked examples. When you're first learning a new concept, seeing those step-by-step solutions can be incredibly helpful. But as you gain expertise, those same detailed explanations might start to feel redundant.
Like they're stating the obvious and slowing you down.
Precisely. And that's because as we develop expertise, we start to chunk information differently. We can hold more in mind at once, and we can make connections more quickly. So those detailed explanations that were once necessary become extra baggage.
So it's like we've built up our mental muscles, and now we're ready to lift heavier weights without all the extra support.
That's a great way to put it. And that's where the idea of guidance fading comes in. This is an instructional approach, where the amount of support and guidance is gradually reduced as the learner becomes more proficient. So you might start with lots of work examples, then move to partially completed problems, and eventually to fully independent problem solving.
It's like taking off the training wheels as we become more confident writers.
Exactly. Good instruction should adapt to the learner's changing needs, providing the right level of support at each stage of the learning process. Now, before we wrap up, I want to touch on two more interesting cognitive load effects: the imagination effect and the self-explanation effect.
Oh, those sound like active learning strategies that we can use ourselves. Tell us more about those.
These effects highlight the power of actively engaging with the material mentally, rather than just passively receiving it. The imagination effect is all about the benefits of trying to visualize a concept or process in your mind. And the self-explanation effect emphasizes the power of explaining a concept to yourself in your own words.
So it's not just about reading or listening, but about actively creating those mental models and verbal explanations.
Exactly. And the theory suggests that these active strategies can be particularly helpful when dealing with material that has high element interactivity.
Because they force us to really grapple with those interconnected ideas and make those connections more explicit in our minds.
Precisely.
Hmm.
By actively engaging with the material, we're essentially directing our cognitive resources that germane load towards the most important elements. And that can help us to organize the information more effectively, to build those deeper connections, and ultimately to understand it more deeply.
So it's not just about putting in the time, it's about using that time effectively by actively engaging with the material. Now, before we go, I want to bring this all back to our listeners. Why should they care about cognitive load theory? How can they use this information to become more effective learners?
Understanding cognitive load theory gives you a powerful framework for thinking about how you learn best. It helps you recognize when you're dealing with inherently complex material, and it makes you more aware of the ways that poor instruction can add unnecessary mental burden. And armed with that knowledge, you can start making more strategic choices about how you approach learning.
So we can become more aware of our own cognitive processes and use that awareness to optimize our learning.
Exactly. If you know that you're facing a topic with high intrinsic load, you can anticipate that you might need to break it down into smaller chunks, look for clear explanations, or maybe even use some of those active learning strategies like imagination or self-explanation.
And we can also be more critical consumers of learning materials.
Absolutely. If you're constantly having to flip between pages or if you're drowning in redundant information, you can recognize that as extraneous load and start looking for ways to streamline the material for yourself.
Maybe try creating your own integrated diagrams or summarizing the key points in your own words.
Exactly. The key takeaway here is that understanding cognitive load theory gives you a powerful set of tools for taking control of your learning and making it more efficient and less overwhelming. It's all about working smarter, not just harder.
It's about maximizing that germane load, that mental effort that truly leads to understanding.
Well, this has been a really insightful deep dive into the world of cognitive load theory. We've covered a lot of ground, but the core message is clear. Element interactivity matters. It helps us understand why some things are inherently harder to learn and how poor instruction can make it even harder.
Absolutely. And by being mindful of these different types of cognitive load, intrinsic, extraneous, and germane, we can become more conscious and strategic learners.
So as you continue your own learning journeys, we encourage you to think about the materials you're using. Are there any unnecessary hurdles that are adding to your cognitive load? Are there ways you could simplify the information, make it more integrated, or use active strategies to really engage with those core concepts? And I'd also encourage you to reflect on your past learning experiences. Think about times when you felt overwhelmed or frustrated. Could cognitive load have played a role? Understanding these principles can really transform how you approach learning in the future.
We hope this deep dive has given you some new insights and tools to help you become more effective learners. We'll be back soon with more explorations into the fascinating world of learning and cognition.